Okay, here we are continuing in our 7.4 lectures. This is lecture number 2. If you're trying to do number 23 in your textbook, then this first example would be perfect for you. So how do we find the magnitude of a resultant? So in number 23 it says use the parallelogram rule to find the magnitude of the resultant force for the two forces shown in each figure. Round answers to the nearest tenth. So a parallelogram rule says that if you have your two forces, then if you draw yourself a parallelogram, the diagonal that goes across there is going to end up being your resultant. And so before I had said in the other lecture head to toe for the vectors. And so if you were to draw the 48-pound vector along this side, it's the exact same vector because it has the same magnitude and the same direction as this other side. And so you still see that you have a head-to-toe connection here, start to end connection here between the two vectors. Okay, so here you have a force of 32 and a force of 48, and you're trying to find this vector v, which is the resultant vector. The resultant vector is the sum of the two vectors. So what you would want to do is you would actually want to go ahead and draw this other side, and then using the fact that the two consecutive angles of a parallelogram are same side interior angles and therefore must be supplementary, we can figure out that this angle Q has to be 104 degrees. So the 104 degrees comes from, again, the fact that when you have a parallelogram, you have two parallel sides cut by a transversal, and so you have same side interior angles that add up to 180. So just remember that every time you have consecutive angles of a parallelogram, they will add up to 180. So what we're going to do is we're going to focus just on this triangle, okay? So consider that same triangle again. One of the sides is 32. One of the sides is 48. And then the angle right here between those two sides is 104 degrees. This should remind you very much of the law of cosines. So we're just trying to find v right here. We're going to use the law of cosines to do that. So that's exactly what we do right here. Using the law of cosines, we say that vector v, and here we don't have a little vector symbol over v, but you will notice that v is a bold letter. So sometimes textbooks will use bold letters. Since in your handwriting you do not have a bold font for handwriting, what you will need to do for your handwriting is go ahead and give v that vector top right there. So when you write this out by hand, you're going to be writing it like that. So what are these absolute value bars for? These absolute value bars are the way we write magnitude. So the physical vector itself is v with this little top. Okay, that's the physical vector itself. The magnitude of that vector, the length of that vector, is a plain old number. And that's represented with the absolute value bars, so to speak, on either side. Okay, so we just use law of cosines, and then once you get the result, 4071, you take the square root of both sides, and you find that the magnitude is 64. In this problem, it's 64 newtons. In the problem of number 23, you're going to have a resultant that is in terms of pounds. Now, when you get to number 31, you will see that you have two tugboats pulling a disabled speedboat. So let's look at this diagram and see how this relates to two tugboats. Okay, so here's tugboat number 1, here's tugboat number 2. Both of these tugboats are pulling with their own force. This tugboat's pulling with a little bit larger of a force than this one. And then here's this disabled boat that they are pulling in the water. So what we see here is that the two tugboats together are pulling in different directions with different strengths, but their pulling is pulling to the right. So the resultant vector the result of these two tugboats working hard together is going to be this positive vector v. This positive vector v is the resultant of these two tugboats working together. They need to pull at a force that is going to move this other boat, but this other boat is pulling against them with its own force. And so the equilibrant is this opposite. The equilibrant is going the opposite direction. Okay, so you have here in green, you have over here in green this positive vector v, and this is the resultant, and then over here in green and purple, you have negative v, which is the equilibrant. Now, one of the things to notice is that negative v and positive v are opposites of each other, so that means that they have the exact same length and exact opposite directions. So all you need to do to figure out the magnitude of the equilibrant is find the magnitude of the resultant, which is what we did in problem number 23, or in this lecture in example 1. So that's how you get the magnitude of your equilibrant. To get the direction, just find the direction of the resultant and then go back the other way, the opposite direction. So let's see how this is worked out. To find the magnitude, we use the law of cosines, just as we did in the previous problem. So here's how we get the magnitude. Now, what's happening here is the 180 minus 98 is that in the original problem here, for example 2, it tells us that the angle between the two is 98 degrees. So in the original problem, the two tugboats together, or the two forces in this problem can be anything, are a 98 degree angle between the two. And that's how we get the 82, is just using the fact that the two consecutive angles of a parallelogram have to add up to 180. But we don't really want the 98 in our diagram. We care about the 82 being in the diagram because that's how we get our triangle right here. And this triangle right here has a side length of 54. You see right here we have a side length of 54 because this purple vector right here is the same as this 54 vector down there. So here are the two sides of my triangle and the angle included, and that's how we're doing the law of cosines. Now what about the direction? To get the direction, we're going to be using a law of sines. So all we have to do is find this required angle alpha. And this required angle alpha is going to be the supplement of the little angle in here. Let me make this diagram a little bigger here. So the little tiny angle inside, angle CAB, is going to be this angle right here. That is angle CAB. So angle CAB comes from CAB. Once you find this angle, to get alpha, you simply subtract that angle from 180 degrees because they are supplements. And to get little angle here, this little purple angle, CAB, you just use the law of sines. So use the law of cosines to figure out the magnitude, and then you use the law of sines to ultimately figure out the direction. So that's that problem, and that will help you then with number 31. To help you with problem number 33, I'm going to work through number 34. So the first thing we have to do is draw a diagram based off the information that we are given. We are told we have two vectors acting together, and we have a resultant vector, but we do not know the angle between the two vectors. So let's look at the two vectors acting together. So we have two different forces, 128 pounds and 253 pounds. We don't know the angle between them, so when you draw your diagram, you just have to guess. So any sort of diagram that looks like this should be fine. Next, we're going to find the whole parallelogram by connecting lines that are parallel to these lines. So this one right here is going to be parallel and with the same length. So this would also have to be 253 pounds. And then we have this other side. The opposite sides of a parallelogram are congruent. So you just fill in your parallelogram, taking the two vectors that you have. There's one other piece of information that we have, and that we know the resultant vector of these two vectors is 320 pounds. So the resultant is going to go across this long diagonal, 320 pounds for my resultant. What I don't know is the angle between the two vectors. The angle between the two vectors, the angle I'm looking for, is this angle right here. So here, this angle, the orange one, is the answer to my problem. This is what I want. Okay? Now, I'm not going to solve for that directly. I'm going to solve for the supplement of that angle. Namely, I'm going to solve for an angle over here. Let's say I call this angle theta. This angle theta I can find using the law of cosines, right? So 320 squared is equal to 128 squared plus 253 squared minus 2 times 128, 253, cosine of the angle opposite this side right here, and that would be theta. So cosine of theta. So by using the law of cosines, I can solve for theta. Notice again that the side opposite theta is the one that goes on the far side of the equation, whereas theta is on the far right. So now I'm going to subtract these two numbers from 320. So I have 320 squared minus 128 squared minus 253 squared. And now I can rewrite this as 22007 is equal to negative 2 times 128, 253 cosine theta. And now I'm going to divide both sides by this coefficient here, negative 2 times 128 times 253. I encourage you to work along with me as I do these problems. So we have negative 0.33978 is equal to cosine of theta. So now I do inverse cosine. I need to make sure that I am not in radians. That would be bad. I need to be in degrees. So I am inverse cosining the answer. Theta then is approximately 109.86 degrees. If theta is 109.86 degrees, I can subtract theta from 180, and that would give me my answer, because these two consecutive angles of the parallelogram must be supplementary. And so when you subtract it, you get 70.14 as the answer. Let me check to make sure that that is correct. Well, they did 70.1 degrees. They did not tell me to use any specific digits, but since the numbers had 3 significant digits, 128, 253, then 70.1 also has 3 significant digits. So of course, when we use MyOpenMath, they're going to tell us what to round to. So don't stress too much about significant digits, but that's why they chose to round to that place. Okay, now for question number 35, you'll notice in the book that it's highlighted with green, the problem number. Anytime you have a problem number highlighted with green, that means that I am posting the solution on Blackboard. So you can find the solution to that on Blackboard. So do 35 completely by yourself first, and then check the solution on Blackboard. Your last textbook problem is number 39, which is force needed for a monolith. You're supposed to find how much force is required to hold a 60-ton monolith on a causeway. Now that is no different than trying to find the force of keeping a car parked on a hill. So ultimately just transfer the techniques used for this problem to your monolith problem number 39 and you will be fine. So what we have here is a 2,500 pound car instead of a 60-ton monolith, and we have a 12-degree angle hill instead of a 2.3-degree angle causeway. And the force of gravity is going straight down, right? So the force required to keep it on the hill is represented by this pink vector. That would be the force required to keep it on the hill. Now you can break up that pink vector into two components. You have the force of gravity, which is going straight down, and then you have this other force BC is the force of the car acting on the hill itself. So vector BC, as I just said, is representing the force with which the weight of the car pushes against the hill. And BF, as I had just already said, represents the force required to hold the car in place. And so what we want to do is figure out BF by looking at these two component vectors here and the fact that we have a right triangle. So instead of drawing the 12-degree angle here, we want to put it right here. These are going to be similar triangles, and they're just oriented in a different way. Now, BF, this force right here on the hill itself, is going to be equal to the force right here, which is this far side of a right triangle. So we can use cosine. You see, we got a 12-degree angle, sine, not cosine. We have the opposite side that's unknown, but we do know the hypotenuse. As it turns out, the 2,500, the weight, which is from gravity, is the hypotenuse of this right triangle. So take this diagram and just apply it to your monolith problem and just change the numbers and you'll be golden. Alright, so there's a further explanation if you want to pause and read that. But ultimately, I just want to get to this part right here. And we zoom in on this right triangle that we have here. We use a basic sine SOHCAHTOA because we have a right triangle. And so we can find AC by using simple sine ratio. And then that will tell us the force to keep the car parked on the hill. Now remember, when you get done with your problems in the book, all of the answers are going to be in the back of the book. So make sure you check your answers to make sure you get your problems right.